it will be a similar setup to part A. Where we're going to have a infinite straight wire, but instead of a square loop above, we're going to have a triangular loop above, and each of its sides is going to be a distance A. With a current I. Distance S above this infinite wire. So similarly to part A, we can break this up into segments, with segment 1 being on the bottom, segment 2, and segment 3. Starting with segment 1, very similar to part A, we can find the magnetic field from Ampere's law times I. And this is going to be B times 2 pi s is equal to mu naught I. B is equal to mu naught I over 2 pi s. Z direction, out of page. Now we can find the force the same way that we found in the first part. Doing the path integral of dl, it's similarly, if we make our origin here, it's going to be going from A to 0, dx x hat crossed with mu naught I 2 pi s z hat. And that gives us all of these constants can come out, I squared mu naught over 2 pi s, and x hat cross z hat gives us negative y hat. Dx is A to 0 dx, and we're left with I squared mu naught 2 pi s times A in the y hat direction. So same thing as part A for segment 1. Now, when we get into segment 2, it's a little bit different. Two and 3. So, first, we find the magnetic field using Ampere's law. B times 2 pi s plus y. Since it's going to be a variable distance from this wire, is equal to mu naught I, leaving us with mu naught I over 2 pi s plus y, z hat direction out of page. Now we can find the force. But first, if we look at our triangular loop and we're making this as our origin point, then we can make a set of coordinates here. This being in the y direction, this being in the x direction. And since we know that this is an equilateral triangle, this is going to be a 60-degree angle right here. Maybe it'll be easier to see if I make it a little bit bigger. this is going to be 60 degrees, and this being 30 degrees. So we know that this would already be a over 2, and we know that this distance to the top would be a times root 3 over 2, just using our trig functions. And similarly, we can find the equations of these lines. So right here, we can find the equation for segment 2. Just erase this a little bit, just to give us some more space. Now, we can find this equation of this line of segment 2 from using trig functions again. So y is going to be equal to tan pi over 3, or 60 degrees here, times x. And similarly, since this is going to be a negative slope, it's going to be negative tan pi over 3. And since it's a bit a ways from the origin, it's going to be x minus a. Distance a from the origin, passing through rather. This is going to be for your segment 3 equation, rather. And we know that tan pi over 3 is root 3, so y is equal to root 3x, and y is equal to negative root 3 x minus a. So these equations can help us when we're actually doing the path integrals for the force. Equal to, so when we find the force, we can use the path integral, and since this path is going in different directions, we can make our dl dx x hat plus dy y hat plus dz z hat, crossing with the magnetic field that we got previously. And then we will get our equation. To be I out in the front and 2 different path integrals. Well, 3 different path integrals. The first one, mu naught I, just distributing this constant into each of them. 2 pi s plus y dx. X hat crossed with z hat is going to be negative y hat plus the path integral mu naught I over 2 pi s plus y dy. And y hat crossed with z hat gives us x hat. And finally, for dz times z hat crossed with z hat just gives us 0. So now we can individually find these components. So f of x would be I times the path integral from mu naught I 2 pi s plus y dx, and this is going to be for segment 2, which means from segment 2 for x, it's going to be going from 0 to a times root 3 over 2. So we can write that in here. Plus the same integral, s plus y dx. And this is for segment 3. Oh, I guess rather, this is for dy, for the x component. This would have negative here, negative here. And for the third segment, rather, it's going to be going from a root 3 over 2 to 0. So if we write that in here, 0, we'll notice that these are equal and opposite if we change these bounds, which means that this just goes to 0 and the x components cancel out with each other. This isn't unit vector. Now for fy, the fy component is going to be these shouldn't be negative. For the y component, we can take the mu naught I over 2 pi out, just because they're all constants. And since we already have an I, we're going to get a I squared. And there's also a negative here in this y component, which means we can take that out too, out of both segments. That's going to be times 1 over s plus y dx, and this is going to be for segment 2. So for segment 2, it's going to be going from 0 to a over 2. So 0 to a over 2. And since we know the equations that we found before, y is equal to root 3 times x, then we can plug that in here. That's for our segment 2 equation. And then similarly, for our segment 3 equation, we're going to go from a over 2 to a, and then 1 over s plus y, and our y in this segment 3 case is negative root 3 times x minus a. Root 3x plus root 3a dx. Now, write this on our new page to get some more space. Now we can find both of these integrals using u sub, where u is s plus root 3x, du is equal to root 3 dx, u prime is going to be equal to u prime is equal to s minus root 3x plus root 3a, du prime is going to be equal to negative root 3 dx. And we can find these bounds. So 0, if we plug this in, s going to a times root 3 over 2. And for this integral, if we plug in a over 2, it's going to give us, this is plus s, rather. S plus a times root 3 over 2. And this goes to, if we plug in a to here, these two cancel, leaving us just with s, which means that we're going to get two integrals. One going from s to s plus a root 3 over 2, 1 over u du, with a 1 over root 3 in the front. And this is going to be minus 1 over root 3 in the front. And this one's going from s plus a root 3 over 2 to s, 1 over u prime du prime. And if we look at these integrals, if we switch these bounds, this gives us a negative, which means we can combine them into one integral, leaving us with 2 over root 3, s plus a root 3 over 2, 1 over u du. These 2's cancel, and we get root 3 over pi, and then we can do a natural log for this integral, or we get a natural log for this integral, and that leaves us with s plus a root 3 over 2 minus s, which means we can combine it into one natural log, leaving us with our answer. We can simplify a little bit more. As canceling these out with 1 plus root 3 over 2 a over s. Now that we found our y components for segments 2 and 3, we can find the net force on the original triangle, or the triangular loop above this wire, by adding up our forces. The first force being I squared mu naught a over 2 pi s y hat direction minus mu naught I squared root 3 pi times the natural log of 1 plus root 3 over 2 a over s in the y hat direction. And this leaves us with and I just took out these terms from these and shifted some things around, and that gives us our net force. Thank you.